Hello, am I audible?
Yes, sir.
Okay, great. Okay, so is there a lag in my audio?
Sir, you're not writing anything, so we can't. Hello, sir.
Hello, am I audible?
Yes, sir, you're audible.
Okay, great. Yeah, seems to be a bit of a network problem. Okay, so I hope you can see my screen. Let's start. Okay, so previously we were discussing the data compression problem, and the goal is to compress a source or a raw file into a compressed file which takes less space than the original file. So we have a source file xn, which at least for now we'll assume that this is IID. So each xi is independent and identically distributed according to a known distribution px. Such a source is also called a memoryless source. And we encode this to a string of k bits, which we call the compressed file. And the goal is to be able to reconstruct xn from ck. Right? And in the previous class, we saw that if you're doing variable length compression, then the minimum compression rate, the minimum achievable rate of compression, is less than or equal to h of xn over n. So the asymptotic minimum average compression rate is basically the limit as n tends to infinity of the entropy divided by n. So this quantity, this limit, is called the entropy rate. And in fact, in the previous class, when we derived this bound, we really did not make any assumption on the distribution of the source. So this statement that the minimum rate of compression is less than or equal to h of xn by n, this is true for any source, whether it is memoryless or not. It could even be a Markov source. So as long as this limit exists, the minimum rate of compression is less than or equal to the entropy rate. In fact, we'll see a little later on in this course that the minimum rate of compression is not just less than or equal to the entropy rate, it is exactly equal to the entropy rate. So any compression scheme, asymptotically, it cannot achieve a rate which is less than the entropy rate. And recall the definition of entropy. So this is the summation of overall possible sequences xn of p of xn log 1 over p of xn. Right, so this is the entropy of xn. Now note that I've used this particular notation for the entropy h of xn, although this is not good notation. So really, the entropy is a function of the distribution pxn and not of the random variable xn. But unfortunately, in the literature and in most textbooks, you will see this notation h of xn. So that is what I will continue to use. But a better notation is really h of pxn, since the entropy is really a function of pxn and not xn. It's a deterministic quantity and it depends only on the probability distribution. In the previous class, we also simplified h of xn for IID sources. noticing that P of xn is simply the product over all P of xi's, we could show that h of xn is simply equal to n times h of x1, and therefore for an IID source, the minimum rate of compression is less than or equal to h of x1. Right? So this is basically h of px. So I'll sometimes interchange between these two notations, h of x and h of px, but both basically mean the same thing. Right? So this is basic. This is equal to the summation over all possible x in the alphabet of p of x log 1 over p of x, and this is measured in bits. So we say that the entropy, so the entropy has a number, but we also say that so h of so for a given probability distribution, we say that the entropy of this particular random variable drawn from this distribution is 1 bit or 1.5 bits or 3 bits. So entropy is measured in bits. All right. So any questions up till now? Okay, so one other point that we need to note in the definition of entropy is that this really, I should be a little more careful when I'm defining the entropy over here. So h of px or h of x, so this is actually equal to the summation over all x with positive probability. So note that if so this is also equal to, another way of writing this is minus summation over all x in x of p of x log p of x. But really 0 log 0 is not defined. So if a particular symbol has 0 probability, then it basically contributes a 0 to the entropy. So really the definition of entropy should have been the summation over all x in x such that p of x is strictly greater than 0 of p of x log p of x. But we'll get around this particular issue by redefining x log x. So we'll say that, or alpha log alpha, we'll say that this is 0 if alpha is equal to 0. All right, and you can also verify this. So you can verify that the limit as alpha tends to 0 of alpha log alpha is also equal to 0. So we will redefine x log x or alpha log alpha at 0 just to make sure that it's well defined and continuous in the range 0 to infinity. Okay, so any questions? Okay, so the entropy of a source, just 1 second. Yeah. So the entropy of a source, in some sense, captures the amount of information in that particular random variable. As in the first 2 classes, I mentioned that the minimum rate of compression is at least heuristically connected to the amount of information in the source. So, so that is one connection between the information content of a random variable and the entropy. So we will say that the information contained in a particular random variable x is equal to the entropy of x. Okay, but there are other ways of studying entropy. Note that the term entropy really came up as a fundamental limit of the data compression problem. This is the minimum rate of compressing an IID source drawn according to the distribution Px. But we can also arrive at the entropy function using a different approach. So there is a so-called axiomatic approach. There's an axiomatic approach where you say that so we define certain properties of what a measure of information would need to satisfy, and then try to find out what functions satisfy this particular property. So you can take a look at exercise 2.46 in the book by Cover and Thomas. To see one set of axioms. So you look at all possible functions which satisfy a set of properties, and you can show that the entropy is the unique function of the distribution which satisfies these properties. So what is given in exercise 2.46 in Cover and Thomas is not the only set of axioms that lead you to the entropy. There are other axiomatic definitions which are all equivalent, and all of these give you the same function. Okay. All right. So now that we've defined entropy and we've seen its connection to information and data compression, let's have a little quiz. I'll put up the link to the quiz in the chat box as well as Piazza.
Hello, sir.
Yes.
Sir, that Rmin should be greater than or equal to, right?
Sorry.
The
correct. Okay. So what Sachin is saying is that Rmin should be greater than or equal to. Actually, that's not true. So what did we do in the previous class? So in the previous class, we designed a compression algorithm. Right? We designed one compression algorithm, and we noted that the rate of compression achieved by that particular algorithm was equal to this quantity. Am I right?
Yes, sir.
Right. So that is one particular compression algorithm, and Rmin is the minimum over all possible compression algorithms. Right. So I give just one algorithm. So the minimum rate of compression can only be less than or equal to the rate achieved by that particular algorithm. Correct?
Sir, we want the rate as minimum as possible, right?
Correct.
So if we say this, then the rate can become 0 also, right?
So what have we? So we have shown that the rate of the rate of compression achieved using that particular algorithm that I described in the previous class is equal to the entropy rate. Now, maybe there is an algorithm which achieves an asymptotic rate which is less than this, but that is something that I have not shown. Right? We have not really formally proved this, but in fact, it is true that you cannot do any better than this. Asymptotically, you cannot achieve a rate which is less than the entropy rate, but that is something that I have not proved yet.
Sir, in the RHS, that is only the entropy rate, right? So
the right hand side, yes, that is the entropy rate.
So
But
R
what is
minimum can be equal to or greater than, but cannot reduce further from it, right?
why?
So because it is the minimum achievable rate, the entropy rate, right?
But that's not something that I have shown yet, right? I have not proved that it is the minimum rate of
Okay.
compression, right? So
Okay,
I have
sir.
only proved that it is less than or equal to this, but as you mentioned, it is equal to the entropy rate, but that is something that we have not proved yet. You can show a similar inequality that that R min is also greater than or equal to the limit as n tends to infinity of h of xn over n. But this is something that I have not proved yet, but I'm just stating it now. So the minimum rate of compression, in fact, is equal to the entropy rate for stationary and ergodic sources. But we will see this inequality, the red inequality, later on in this course. So we need to still develop some more tools in order to be able to prove this particular statement.
Okay, sir.
Okay. Okay, so before we proceed further, I just give you the link to the quiz. So we'll spend maybe 3 to 4 minutes on that and then proceed. So here it is. So I'll give you maybe 1 more minute. Okay, so let's continue. Right, so any questions so far?
Sir,
Yes.
the previous question itself, like the R minimum, I didn't still understand how it is less than or equal to. I still feel it's greater than or equal to. From the last time assumption, we took h of R of x should be like h by n plus some delta.
Correct.
So
So I'm only talking about asymptotically, right? So as n tends to infinity, so it's h of xn plus delta, right? And the delta divided by n tends to 0 as n tends to infinity. Do you agree? So let's go back. Where was
yes,
it?
sir.
Yeah. So it's really h of xn plus, so it's h of xn plus what was it, log of log I, right? So it's 2 log I, which is certainly less than or equal. So log I is less than or equal to n. Do you
Yes.
agree?
Yes, sir.
So it's at most some constant times log n divided by n, right?
Yes, sir.
So as n tends to infinity, this is still equal to the limit as n tends to infinity of h of xn by n. So it's limit as n tends to infinity of h of xn by n plus limit of as n tends to infinity of constant times log n by n, and log n by n tends to 0 as n tends to infinity, right?
Yes, sir.
So it's equal to 0.
Yes, sir.
So agree. So this is the again. I'm talking about the asymptotic rate of compression. I would like to clarify that this is not the minimum compressed length that we can achieve. Okay. So the actual compressed length for a given n may be much smaller than what we have achieved over here. It is in fact it's different from h of xn by n, but all that I'm claiming is that as n tends to infinity, the limiting average compression rate is less than, so at least from what we have shown, it is less than or equal to the entropy rate.
Got it, sir.
Correct. And we'll see a proof where the minimum, I mean later on. So once we've learned some more tools, we'll see how to prove that the minimum rate of compression is actually is also greater than or equal to the entropy. Okay, any other questions?
So
Yes.
in the quiz, the Bernoulli 0.5 random variable, how can
Correct.
the entropy be 1?
So what's the definition of entropy? So it's minus summation over all x, px log to base 2 of px, right?
Yes, so 1 by 2 log 1 by
Correct.
2.
Correct. But what is
Oh,
log 1
log
by
is to
2?
the log is to the base 2.
Yeah. Right. So I've always been using log to base 2 everywhere, right? Any other questions?
Sir,
Yes.
that's why half into log is log to the base 2, right?
Yes.
That log part is 1
Correct.
and the answer should be half, right? 0.5.
So it's sum over all x, right? So it's half log half plus
Yeah.
half log half. So it's minus half log half minus half log half.
Okay,
Right? So
for
it's minus
summation.
half plus half. Yes.
Okay, sir.
Any other questions? Okay. So let's notice some interesting properties of the entropy. So firstly, can you say something about the entropy? Is it always greater than or equal to 0, or can it be less than 0? What can you say?
Always positive, sir.
Why?
Because it is the information content, right? Information cannot be negative.
Correct. So that's an intuitive explanation.
And also here the probability lies between 0 to 1. So as
Correct.
per the formula also, the negative sign will
Sure.
cancel and be positive.
Correct. So for all x, we have that p of x is less than or equal to 1 and greater than or equal to 0. So p of x, so 1 over p of x is between 1 and infinity. infinity. So log 1 over p of x is between 0 and infinity. So p of x log p of x is between 0 and infinity, and therefore the sum is also between 0 and infinity. In fact, we'll show a little bit later in the course, maybe in the next week or so, that for a given input distribution, the upper bound, the upper bound is much smaller than infinity. It is in fact less than or equal to log of the cardinality of x. And can you say why this is expected? Using the idea of compression, of course.
So most information contained when the distribution.
Sorry, your voice seems to be breaking. Could you please repeat?
So most information contained when the distribution is uniform.
Correct. But maybe you're close, but can you maybe reword it, put it in a slightly different way? So what is log x?
So maybe it's the worst case wherein it becomes equal to the fixed length encode. And
correct. So the maximum number of bits you need to use to encode each symbol is log x, right? And any compression algorithm should be able to achieve a rate which is less than or equal to log x. Right? So without any sort of compression, just directly representing each sequence in binary requires n log. So C of n log size of x, right? So the rate is this divided by n, which is basically log cardinality of x. So since the entropy is the minimum rate of compression, it should necessarily be less than or equal to log cardinality of x. But we'll see a more mathematical proof of this later on in this course. So this is one property, that the entropy is non-negative, and that is something that we would expect, because we are saying that the entropy is the information content of a source or the minimum rate of compression, and this has to be greater than or equal to 0. Another property of the entropy is that it is symmetric in the distribution. So if you interchange the probabilities of two different symbols, the entropy still remains the same. So if you have a distribution, say half, 1/4, 1/4. So let's say you have three symbols, A, B, and C, where A takes probability half, B takes probability 1/4, and C takes probability 1/4. Then you get something, the entropy is some particular value. But the entropy of this is the same as if you had A taking probability 1/4, B taking probability half, and C taking probability 1/4. So if you exchange the probabilities of different symbols, the entropy still remains the same. So it is symmetric. Right? Okay. So now we'll any questions so far? Okay, so now we'll just change, sort of switch gears a bit, and let me see. Yeah, you can see the screen. I'm projecting a file here of some slides. Is it visible?
Yes, sir.
Okay, great. So our discussion in the last few classes was mainly on data compression, and we saw that the entropy arises as a fundamental limit to the data compression problem. Now we'll explore another information quantity by looking at a slightly different problem, and that is communication through a noisy channel. So I define the foremost a nice problem of how do you communicate reliably in a noisy channel, and we'll see what is the maximum rate at which we can communicate reliably across a certain noisy channel, and we'll see what is the fundamental limit over there. All right. So let's briefly recall what a digital communication system looks like. Now, I guess some of you are electrical engineering students, so you would have taken a course in digital communication. Some of you may have not, particularly maybe those in AI or engineering physics and others, but doesn't matter. I won't assume sort of any prerequisites regarding digital communications. But all that you need to know is that the goal is, of course, to communicate across a noisy medium. So, for example, let's as an example, you can consider communicating in just cellular communication, perhaps. So, what is the problem over there? You have a source signal, which could be just your voice. Now, you can view this as a continuous time signal. And this needs to be processed by a digital system. So it is typically first sampled and then quantized. So you convert your speech signal or even a video signal into a stream of bits by first sampling the sequence and then quantizing it using a finite number of bits to represent each symbol. And once you have a stream of bits, you first compress it. So this is the source coding block. And once you've done source coding, you add some redundancy. So the goal is to transmit this across a noisy medium. And if we transmit it as is, a lot of the bits are going to get corrupted. So if the bits are corrupted, then there's no way to recover the source signal. So you add some redundancy using this block called channel coding, and then you modulate it. Now we are operating in the digital domain over here, so everything is in terms of bits. But in order to transmit it across space, you need to first convert it to a continuous time signal. So you modulate it using sine waves and cosine waves, and then transmit it across the antenna, and it passes through the channel. The receiver has a similar set of blocks. So it receives a continuous time signal. This is first demodulated. So you convert the sines and cosines back into a stream of bits. You remove whatever redundancy that you had added. You decompress the source, and then you reconstruct the source. So you have a stream of bits, and then you do reconstruction, digital to analog conversion, and you get back the speech signal that you hear the recipient hears on his speaker. So this is the basic block diagram of a digital communication system, and we've already explored two of these blocks, the source encoder and the source decoder. Now, in order to ensure that you can reliably communicate, you can somehow get rid of the effects of noise. As I mentioned, you need to add a certain amount of redundancy. So it seems a bit weird that you're first removing redundancy in the source coding block, you're first compressing the block, but then you're adding an additional source of, you're adding some redundancy in order to counteract the effects of noise. Now, there are methods of doing this jointly. So you can do what is called joint source and channel coding, where instead of splitting these into two blocks, you have a single block which takes care of both joint compression and adding redundancy to mitigate the effects of noise. But the advantage of splitting it into two separate blocks, source coding and channel coding, is that each of these blocks can operate separately irrespective of what the input is. So for the source coding block, it really matters what the input is, right? So in order to compress, the compression algorithm you would use for a speech signal would be different from the compression algorithm you would use, for example, for an image signal. But for the channel coding block, it doesn't really matter. So we can design the channel coding block without caring about whether we're transmitting a speech signal or an image or a video. So this channel coding block can be oblivious to the source signal, and that's the advantage of having this modular structure where you have separate source coding and channel coding blocks. So even before we describe what we mean by channel coding, it's useful to look at, or at least to give a mathematical definition or a mathematical formulation of communication through a noisy channel. So how do we model a noisy channel? Right? So the way we'll model a noisy channel is through a random structure. So just give me a minute. So any questions so far? All right, so all right. So our goal is to model a noisy channel, and the way we'll do it is the following. So for us, the channel is going to be a black box. So the channel will take as input a sequence xn, maybe a sequence of n bits, right? And it is going to output another sequence of n bits, right? And we'll assume that the output is going to be a random function of the input. So given an xn, we will model the channel as a conditional distribution py given xn. So given each xn, yn is going to be a random variable which will be distributed according to the channel law. or the channel transition probability. Py given xn. Okay. So let's look at the simplest version of a channel where the input is a sequence of bits.
Sir,
Yes, please.
sir, I have doubt that a particular transmitter and receiver can be split into source and channel coding block. How this can be practically achieved?
So, okay. So what do you see as the problem with splitting into a separate source coding and a channel coding block?
Sir, particularly source coding
Mhm.
depends on source signal, and
Correct.
as you told, and the channel
Correct.
coding depends on independent of source signal. So,
Correct.
sir, maybe.
Uh-huh.
So practically, how this can be implemented, sir? I just want to know
So
the
the
rough.
way the channel coding block is implemented. So let's go back. Right. So the way so typically in practice, even in your cell phone, the channel coding block is designed based on this communication medium or the effective discrete channel alone, nothing else. So you don't care about what the source is. You assume that the input to the channel coding block is a sequence of independent and identically distributed, so uniformly distributed bits. That will be our assumption when we design the channel coder and the channel decoder. The source coding block, on the other hand, will be designed purely based on the source signal. So nothing else. So the source coding block is designed assuming that the input is from a given distribution, and the reason why we can sort of split this into a separate source coding block and a channel coding block is the following. So this is something that we've not seen yet, but here's an interesting property of uh, a good source compressor. So let's go back. Yeah. So what does the source coding block do? It takes the input and gives and outputs a compressed file, right? Now, if it's a good compressor, so the other thing we have noted is that the minimum rate of compression is equal to the entropy, correct? So it's h of x. Okay, and the other thing that we've noted is that the entropy is always less than or equal to it's greater than or equal to 0 and less than or equal to log cardinality of x. So if we assume that both the input, if the input is say a Bernoulli sequence, let's assume that the source file is a sequence of bits drawn from some distribution, then the entropy of any binary sequence of any binary random variable is between 0 and 1. Now, if the compressor is a good compressor, if it's an optimal compressor, then what do you expect the distribution of the compressed bits to be? What do you think the compressed bits will look like? So it's going to be a Bernoulli sequence. So any guesses, anyone?
Can you repeat the question?
Okay. So let us consider the problem of compressing a sequence of bits. Okay, so xn is a sequence of n bits. I use a compression algorithm and I get another sequence of k bits where k is less than n. Now, if the compressor is good in the sense that if the compressor is optimal, which means that I cannot compress ck any further, then what do you expect the distribution of the compressed bits to be?
Bernoulli with half probability.
Correct. And why?
Maximum uncertainty.
Correct. So suppose that CK is not Bernoulli half. If the CIs are not Bernoulli half, then it means that I can compress the CK once again to get an even lower rate of compression. Right? If it is not Bernoulli half, if it is say Bernoulli 0.4, then I can use another compression algorithm to compress the Bernoulli 0.4 sequence to something else. So I should be able to achieve an even lower rate of compression. But that sort of contradicts my statement that the compression algorithm I'm using is optimal. So if a compressor is good, then the output of the compressor is going to be a uniformly distributed sequence. Correct? And that is true irrespective of what the source is, whether the source is binary or it's from some other alphabet, whether it's memoryless or it has memory. If we are using an optimal compressor, then the output will always be uniformly distributed. And since we have this nice property of a good compression algorithm, we can assume that the input to the channel coding block is a uniformly distributed sequence of bits, irrespective of which compressor you use. And we will operate under this assumption and then design a source coding and a channel coding block purely based on the statistics of the channel and ignoring what the true source actually is. Does that answer the original question as to why we can split it into separate source coding and channel coding blocks and how we would design it?
Yes, sir. Clear.
Okay. Okay, so going back, now I was talking about how do we model channels, right? And just as in the source compression problem, where we modeled the input file or the source to be a random sequence, when we are dealing with channel coding, we will model the channel or the noisy communication medium as through a conditional distribution. So the input to the channel is xn, the output will be yn, and the channel law completely specifies the distribution of the output given a particular input sequence. So the simplest model is sort of the bit flip channel. So the input is a sequence of bits. You give a sequence of n bits. The output will be another sequence of n bits. And each bit is flipped with a certain probability. So a 0 may be converted to a 1. Some bits are transmitted as they are. Okay, so this is my xn and this is my yn. So what I could do is for each bit, I independently toss a coin. I toss a biased coin, maybe with probability 0.1. So with probability 0.1, a 0 gets converted to a 1. And if it's a 1, then it gets converted to a 0 with probability 0.1. And with probability 0.9, the bit remains as it is. So if the input is a 0, then it remains a 0 with probability 0.9, and it becomes a 1 with probability 0.1. If I transmit a bit 1, then this gets received as bit 1 with probability 0.9, and it gets received as a bit 0 with probability 0.1. So every bit is independently flipped with probability 0.1. This is what is called a binary symmetric channel, and is sort of the simplest channels that one can study. Right? So is this setup clear? Okay. So a more general class of channels is the so-called discrete memoryless channels, where given an input sequence, so suppose that the input to the channel is x1, x2, x3, xn, each xi is independently changed to yi according to a distribution py given x. Right? So you take each xi with probability pyi given xi, you convert it to yi. Okay, and a specific example is this binary symmetric channel over here that I just described, where the transition probabilities p y given x are given as follows. Right? But for more general inputs and outputs, you could govern this. So this could be governed by a separate conditional probability distribution, or channel probability distribution, or the channel transition probabilities py given x. So in the next class, we'll see some examples of different discrete memoryless channels, both with continuous and discrete alphabets. And we'll see, maybe without proof, the fundamental limit that arises. So we'll formally state what the problem is, and then we'll see what is the maximum rate at which we can communicate across a channel of this form, and what is the maximum rate of communication. Any questions? Okay, so if there are no further questions, then we meet in the next class, which will be next Monday.